did that.
We're about to start at 4. Morning, happy Monday. How y'all feeling?
Amazing.
I'm glad to hear. I hope that's true for everyone. And if it isn't true, I hope it becomes true. All right. It is Monday, so my train of thought is very slow to leave the station today. Any questions before we get started? All right. Well, every so often I like to glance at a calendar to make sure that important dates are still in everyone's mind. I remind myself what those important dates are, if I'm being honest.
Important day today.
Huh?
Important day today.
A day to remember, at least. Today is Monday, September 11th. And this week we are starting chapter 4, which is going to be about force of Newton's laws. I'm planning to spend about 2 weeks on this material. Motion is kind of the beginning backbone of the course, and Newton's laws are kind of the secondary backbone of the course. So I'm planning about 2 weeks to make sure that this makes sense to everybody. And then another week or so for the material after that. Chapter 5, energy and work. And then, to keep this on everyone's radar, I'm planning for the first test to be the first week of October. As a reminder, when I say the first week, you take it during lab time. So you show up, like, it'll take the whole week. You show up during lab and take it during that time slot. And lecture that week would be set aside for test review for the most part. So just keeping it on your radar, about a month until our first test. It'll be on the first 5 chapters. Question?
So are the test questions like gonna be more geared toward class, or because the homework sometimes is a little more difficult? So are they gonna be like that intense?
The test questions are not meant to be intense, because the homework is something that you're supposed to be able to work on freely in a comfortable environment with your classmates. The test is something you're meant to do by yourself in an hour. So I write the test questions with that in mind. I write them all myself. They are not designed to trick you. If there's any part of it that's tricky, it's meant to be like the last 10% separate an A from an A+. My test questions are not written to be super tricky to make your life hard. Homework is sometimes tricky because of the context in which you're doing it, but I don't write the test that way. Does that answer the question?
Yes.
Comfortable with this information for now? Okay. So, just keep it on your calendars. Test will be the first week of October, then we have fall break, and then midterm scores go out. Now, for today, hold on. Beginning chapter 4, Newton's laws of motion. This is when we're going to start talking about force and utilizing Newton's laws in our work. Newton's laws are fairly important to both the Western and modern understanding of physics. Isaac Newton, pretty smart guy, and he didn't invent gravity. I want to kind of clear up that misconception right now, because like, objects fall independent of whether Newton realized them or not. Like, you've seen this happen your whole lives, right? Newton didn't invent gravity. Newton didn't invent motion. He just came up with and wrote down math for it. And he wasn't the first guy to do so. People have been describing gravity for centuries before him. He's just the first European that got famous for it. That said, his formulas are very good and still used today, and that's why we're going to be talking about them. So these first 3 laws of motion are going to help define the rest of the course. And as I said at the beginning of the course, you've seen all these things happen before. You have witnessed physics occur around you. You've been using force, observing motion. You know these three things, at the very least subconsciously. But I need to make sure that you are aware when I refer to the laws of motion by number, what things you've observed are referred to by each law. So the purpose of these laws is not to teach you something all new, it's to teach you what things you already know refer to which arbitrary number. So that when I say the number, it's easier to recall what you know about it to your mind. And I guarantee you heard all of these things out loud before. We're going to look at all of them summarized here, and then we'll spend the next week or so going in depth on the rest of them. Newton's three laws of motion. These all deal with force. And I'm going to define force in a second. First, I want to read the laws out loud, kind of point out to you that it should sound familiar. Newton's laws of motion. Law number 1, an object at rest stays at rest, or an object in constant motion stays in constant motion unless acted upon by an outside force. Law number 2 says net force equals mass times acceleration. Law number 3 says for every action force there is an equal and opposite reaction force. Do these sound familiar? Collective nodding. Good to see. Now, while you're reviewing these and copying them down, I have to tweak my slides very quickly. All right. Now we are going to review each of these in detail. Any questions before I move on? Okay. These all have to do with force, and as a result, it's important to define force as we're going to use it in this class. So, a couple weeks ago, we talked about our first three variables, first three vectors, those being displacement, velocity, and acceleration. This is our newest variable, our newest vector. So it's a new letter that you will be able to use in your formulas. Force. Your formulas will designate this as capital F. So anywhere you see a capital F on your formula sheet, it's referring to force. It is a vector. Force is defined as a vector because every time you've ever pushed on something, you're pushing it in a direction. You cannot push something and that push not be in a direction. Does that make sense? So, force is always a vector. The definition of force is a push or pull that acts on objects with mass to create acceleration. Suppose then I also should define mass, but I'll give you a sec to continue copying things down. So force is a vector. We use it to push and pull on things. The unit of force that we like to use in this class is newtons, named after the scientist whose laws we are discussing. The unit of newtons is abbreviated to uppercase N. Alternate units for newtons include pounds. So wherever you would think to use pounds in a normal American context, newtons is a similar unit. Whatever you do measure in pounds normally, you can also measure in newtons. In this class, we're going to stick to newtons because metric system, but anything that is normally measured in pounds, including weight and also punching force. I know some sports journalists talk about the throwing force or the punching force of various athletes. Those are usually measured in pounds, but we're going to use newtons instead. Feel okay with this information? All right. So, anytime you have ever pushed or pulled anything, you have been using your own muscles to exert force on an object with mass. And I also haven't defined mass formally, so let's do that as well. That's not the slides, but there it is. Let's also define mass, just for the sake of completeness. Mass is a measure of how much stuff is inside of an object. Objects with more mass have more stuff in them. It's going to be lowercase m on your formula sheet. And mass is not a vector. Force is a vector, mass is not a vector. You can't have 2 kilograms up. You can push 2 kilograms upwards, but the 2 kilograms do not inherently point upwards. So mass is not a vector. Measures the amount of matter inside an object. We are going to measure mass primarily in kilograms. I know that we usually use the base unit rather than kilo for most of our formulas, but physicists just decided that every mass unit and every single formula that physicists like to use is in kilograms instead of in grams. I can only imagine they did that to make the numbers smaller, because like a human has a mass of anywhere from about 50 to 150 kilograms. If we tracked that in grams, the numbers would just be 1,000 times bigger. And since physics tends to operate on a human scale rather than like the small piles of dust scale that chemists and biologists use, we use kilograms to keep the numbers smaller. That's my best guess. So anytime you see m in your formulas, it's referring to mass, and you're going to want to use kilograms for its unit. There isn't really an imperial counterpart to mass. We don't really use mass much in a normal American existence. Most people tend to use weight to describe how much matter is in something. So I will continue to elaborate on this for the entire semester. Mass is not the same thing as weight. I don't care how much British television you watch, kilograms is not technically an acceptable unit for weight. Weight is a different thing to mass. Make sure that makes sense when I talk more about gravity. Mass is strictly a measure of how much stuff is inside an object, how many atoms, protons, electrons, etc. are contained within something. So we're defining our force and mass terms to make sure that the laws of motion make sense. How do you guys feel about these definitions? Okay, so after defining force and mass, I want to go back and look at Newton's laws in a little more detail. Make sure that the descriptions of each one of them make sense, and I talk about how we're going to apply all of these laws. Newton's first law of motion states that an object at rest stays at rest, or an object in constant motion stays in constant motion unless acted upon by an outside force. This is commonly referred to as the law of inertia, if you've heard that word before. And what it says is, objects, matter as a whole, if something has mass, it's made of matter, and matter as a whole is really, really lazy. If something is made of matter, it wants to keep doing what it's already doing forever. Case in point, behold, matter. A lot of carbon atoms in my hand right now. I'm going to place this lump of carbon right there. What is it doing? Nothing. How would you define its motion right now? 0. It is not moving. And according to Newton's first law, would you expect it to continue not moving? All right. Newton's first law states that matter does not spontaneously do anything. There's always a trigger, some kind of outside force that causes things to start moving. This object, its own mass, its own inertia, is compelling it to just stay here forever until something, like me, literally forces it to change. All matter wants to keep doing what it's already doing indefinitely until something outside of itself forces it to change. Feel good so far? Okay. This is not only true of remaining still, this is also true of moving at constant velocity. This is kind of hard to observe on planet Earth, but if something is moving, if an object made of mass is in motion, it wants to remain in motion. Your car, while you're driving it, wants to keep rolling forward at the same constant speed. And in fact, if you have cruise control on, it will do that most of the time. Now that said, if you don't have cruise control on and you take your foot off of the gas, what happens to the car? It will eventually slow down, and that's because friction is an outside force. On Earth, because of the ground beneath us and the air around us, there's always friction slowing things down. We can't really avoid it. But friction is an outside force. The friction from the road on your car's tires and the friction from the wind on your car's shell, I forgot the word, is something outside of the car that is exerting a force on it to slow it down. If your car was just not touching the ground and there wasn't any air, it would just keep going. If there wasn't anything to slow it down, it would just go. And that's why things don't slow down in space, where there's no ground and no air to stop you. There is bolts that have flown off of satellites and spaceships orbiting the planet, still going, because there's nothing up there to stop them. Objects in space that have velocity want to keep their velocity. This law says if they're moving, they will stay moving until something stops them. And in space, there is very little to stop you. So not only do things want to stay still, they want to keep moving if they're already moving. To try to give some terrestrial example of this, if you are running, it's easier to keep running at the same speed than it is to change to a different one. Does that kind of feel right? Granted, you have to keep moving your legs and you have to keep burning energy, but it's easier to move at the same speed than it is to speed up. Does that sound right? All right. Again, on Earth, it's hard to observe this because of friction, but objects want to keep moving at the same constant speed. And that's why cruise control works in the first place. Cruise control just has your car's onboard computer calculate just enough thrust to keep it moving at the right speed, just enough to counteract friction. All objects want to keep doing whatever it is they're doing. If I was to give this law a very basic summary to put on your formula sheet, Newton's first law, matter is lazy. Whatever it's already doing, it wants to keep doing. Either moving at constant speed or staying still. How does the first law sound? Okay. So, to apply this to the math that we're going to do in class, because in physics we'd like to take our written descriptions and turn them into formulas. If something isn't accelerating, if A equals 0, comma, then net force equals 0. And an acceleration of 0 refers both to staying still and moving at constant velocity. As long as your speed doesn't change, a is 0. And if a is 0, you remain at constant speed, that means that all of the forces currently acting on you are balanced. This segues nicely into Newton's second law. This law has a verbose paragraph form, but it's often just summarized to this one equation. So if I ask you, what is Newton's second law, you can just point to that on your formula sheet. Several of my students, if I ask them what Newton's second law is, will just say back, "Fma," and you're not wrong. This law says, the net force acting on an object is equal to the mass of that object times its resulting acceleration. This, again, connects back to the first law, because if A is 0, what is your net force? 0. If you're not accelerating for any reason, the net force acting on your object, on your system, is 0. If you want something to start moving, so say I have, again, lump of plastic. If I have this and I want it to begin moving, I have to exert a force on its mass, which is as simple as just using my muscles. Force causes acceleration. The purpose of force is to cause acceleration to matter. So every time you've ever used your own muscles, it is to cause acceleration. Sometimes in the objects around you, sometimes to the matter of your own body, because you're also made of matter. And so moving your arm around is accelerating the matter of your arm. How's that feel? Okay. A couple of finer details to this formula, because we're going to use this formula a lot. I want to make that clear. This specifically says net force is equal to mass times acceleration. I'm going to draw your attention back again to this remote sitting still on this table. What is the net force currently acting on that object? 0. We know this because it is not accelerating. And according to this formula, if you plug in a 0 into A, you're going to get a 0 for sigma F. Now, net force on it is 0. We've observed this. But are there forces acting on that remote currently that are not individually equal to 0? Yes. What types of forces are currently acting on that object? Very good. To demonstrate this, I am going to draw what physicists refer to as a free body diagram. Which is really just a fancy way of saying, I'm going to draw a box and put arrows on it to represent the forces acting on the remote. And it's a box because physicists don't tend to be artists. So, here's our remote. I'm just going to assume it's about 50 grams. And we have determined that there is some force of gravity pulling down on it. That's consistent with our experience on Earth. There's usually a force of gravity pulling things down. As long as you're on Earth, you can't really escape it. So, there's a force currently acting on this remote. Second law says if there's a force, we should see acceleration, right? Why isn't it falling through my table?
Not enough force.
Not enough force to do what? Through the table.
Yeah.
Gravity is not strong enough to tear that remote through the stone of my table. And that's because the table is fighting back. Currently, there's at least 2 forces on that remote that cancel each other out, that add up to 0 because they point in opposite directions. Earth's gravity is pulling my remote down, and the table, out of spite, is pushing the remote up. This happens to you whenever you sit in a chair or stand on the ground, which is 99.9% of the time. Any moment you're not falling, this is happening. Earth is pulling down on you, and likewise, whatever you're standing or sitting on is pushing up, preventing you from falling through the ground.
What is that FG equal?
Force of gravity, sorry. Capital F means force, and there's going to be a lot of different forces in here, so I'm going to give a bunch of different subscripts to them to try to summarize a few of them. F subscript G is what I use for force of gravity. And by the way, force of gravity is an exact synonym to the word weight. Weight is the force of gravity. Some other common ones you will see are Fn. This is something called normal force, which I will define shortly. Sometimes it's just N rather than Fn. And another very common one is Ff for force of friction. So there will be a lot of F's with various subscripts attached to them. So that's just a few. So here, for this remote, we've identified at least 2 forces that are acting on that thing. And secretly, there's going to be even more than this, because, and for very complicated reasons, all matter creates gravity. And that doesn't just include Earth, it also includes humans, because we're made of matter. So right now, your own gravitational fields are pulling the remote towards you, but likewise, my gravitational field is pulling the remote towards me, and air friction is slowing it down in every single direction. And there's also gravity from the moon and Pluto pulling it in a lot of random directions, but those forces are all really tiny and cancel each other out. All the forces acting on that remote are currently canceling out, and we know that because it's not moving. This law says if the acceleration is 0, the net force is 0. And that's why that sigma is there. Net force is 0 for no acceleration. The only time where an object will literally have no forces acting on it is if it's not in this universe. Because as long as you're in the universe, you're some distance from matter and will be subject to some amount of gravity. So there's always force acting on everything. Acceleration of 0, staying still, just means that currently all the forces add up to 0. There are forces, and they have to balance out to remain stationary. You will never be free of gravity. You will never be free of some force acting on you. So in this case, net force, the very definition of net force is just the sum of however many forces are currently acting on the thing. There's not really an official formula for net force. It's just the sum of all forces present. So in this case, we've identified 2. There's gravity pulling down, there's the table pushing up. So the net force currently acting on that remote would be the sum of those 2 things. And since one of them points down and one of them points up, they add up to 0. It's still an addition, it's just plus minus equals 0 in this case. Now, there's not really a formula on your formula sheet for this. Net force is just always the sum of all the forces currently acting on something. You can write that on your formula sheet if you want. It's just not there because it's not really a defined formula. It's not always going to be Fg plus Fn. It's going to be whatever forces are there added together. If they all add up to 0, no acceleration, no change in movement. If they don't add up to 0, then you get acceleration. Because if this isn't 0, A won't be 0 either. Does Does that make sense?
And you said it's just a force plus a force added to each other?
Yes. The definition of net force is every force presently acting on that object added together when taking into consideration vector direction. Force is a vector, we do have to note direction. So here, gravity points down, table force points up, they add up to 0. Okay so far? All right. One more small quirk about this one before moving on. Force and acceleration are both vectors, and in this formula they will have the same direction. The direction of net force is the direction of acceleration, because the net force is what's causing the acceleration. If this thing is normally balanced, and then I come along and disrupt that balance by pushing to your right, if the net force now points to the right, the acceleration takes place to the right. So, these two things are vectors, that's why they're underlined, but mass is not a vector. Mass never points anywhere. Feel okay? All right. Third law, we're not gonna utilize it very much yet. I'll elaborate more on where it comes up as we continue on. But talk a little bit about it for now. I'd say out of all the laws, this is probably the one that gets quoted the most and occasionally misquoted the most. For every action force, there's an equal and opposite reaction force. If you push on something, it's going to push back, and that's why punching things hurts. If you exert force on something, it exerts force back. I lean against wall, I exert force on wall pushes back, and that's why I don't fall over right now. And again, I did Taekwondo, so I tend to think about punching as an example a lot. Punching something usually hurts, because if I exert 10 newtons of force on a board, it exerts 10 newtons of force back. And the board doesn't have nerve endings, whereas I do. Questions? Yes.
So it's just the equal force pushing back on your force?
Correct, and it's always the same number, but in opposite direction.
Yeah.
I'm trying to think of some interesting cases to bring up. When you sit in a chair, your weight pushes down on the chair, and likewise, the chair pushes back up on you with a number equal to your weight. If the chair can hold your weight, it'll exert the same force back and everything works normally. If the chair cannot hold your weight, it's not able to exert enough force back, and therefore the forces on you don't balance out and you accelerate through the chair and it breaks. So, if a force breaks something, it's not able to exert the full required force back. I might be able to punch with a force of, say, 50 newtons, but if a board takes 10 newtons to break, the board is only able to exert 10 newtons back, and that's not enough to stop my fist. And so that's why, in that case, fist goes through board. But if whatever I'm punching can exert the full force back, I do not break through it, and I hurt myself. Feel okay so far? Feel confident with the laws thus far? All right. Let's end today with a little bit of math practice, because at least one of these laws is a formula. Using a baseball bat, you strike a 50-gram baseball with 100 newtons of force. What will the ball's acceleration be?
What's the formula to start this?
I'm glad you asked. Formula we're going to want to use is our new one, force equals mass times acceleration, because we're exerting a force on an object with mass, and we want to know its acceleration. To go through all of my usual steps, though, I have a list over here: mass, force, and we're looking for A. So, three things contained within this formula. I'm going to exert 100 newtons on a 50-gram baseball, and that is going to cause it to accelerate. The whole point of baseball is ball's heading this way, and you want it to accelerate so it's instead going that way. So, we perform algebra and we solve for A. Except there's one teeny tiny problem. In physics, we like kilograms instead of grams. And tragically, now I don't think it's tragic, but if you're used to using grams, it might be tragic. That means that we have to convert these grams into kilograms before we can use them. Every formula I ever give you in this class is going to be designed to use kilograms instead of grams. As a result, for this formula, keep in mind that we measure force in units of newtons. And newtons is enough force, 1 newton, sorry, is enough force to accelerate a 1 kilogram object at a rate of 1 meter per second squared. The very definition of 1 newton depends on using kilograms.
Would be 0.02, right?
Well, hold on. First, how many kilograms is 50 grams?
0.005.
That's one too many zeros, I think. 0.05. Because to go from grams to kilo, King Henry died by, you would need to drag the decimal point 3 places to the left. So if we start at 50, 1, 2, 3. This is the same effect as dividing by 1,000. So instead of 50 grams, we want to use 0.05 kilograms. One baseball does not have a whole lot of matter in it.
So that 0.5 kilograms would go in between the, right there?
Yep. You want to use the 0.05 instead of the 50. I wrote it there to trick you. Sorry. Question?
So is newtons per kilogram the same as meters per second squared?
1 newton is equal to 1 kilogram times 1 meter per second squared. I'll put that over here. 1 newton equals 1 kilogram times 1 meter per second squared. The definition of 1 newton of force is enough force to take a 1 kilogram object and accelerate it at 1 meter per second squared. So 1 newton is actually not an insignificant amount of force. To give you a very quick conversion, you know, I can never remember exactly what it is, so I'm going to look it up and not tell you the wrong number by mistake. I know it's 4 point something pounds per newton. Close.
1 kilogram.
4.44. 1 newton is a, oh no, I had that backwards? Did it? So this is the definition of 1 newton. It's an amount of force to accelerate a 1 kilogram object at 1 meter per second squared. If you're not used to using newtons, 1 newton is about 1 pound is about 4.5 newtons. Whatever your weight is in pounds, multiply it by 0.45, and that tells you instead your weight in newtons. For further sense of scale, I, fairly average adult human male, weigh about 1 kilonewton. So, again, to do this correctly, since the definition of newtons requires that we use kilograms, we're going to use 0.05 instead of 50. Whenever you see grams in this class, your brain should auto-correct it to kilograms before you do anything with it. I apologize to any chemists who prefer thinking in grams. Anyway, this is going to cause our answer to get bigger rather than smaller.
2,000.
Thank you. So the resulting acceleration of this baseball is 2,000 meters per second. I probably made the mass of the baseball too small. Because, yeah, this swing could potentially break the sound barrier. This may not match reality super well. That or it's the Hulk playing baseball, who knows? So, force acting on the mass causes acceleration. Questions? Okay. Next question. A 2,000 kilogram car is driving at a constant velocity of 30 meters per second. What is the net force presently acting on that car? Answer yet? All right. Let's look at our formula. Net force equals mass times acceleration. We've got the mass of the car, 2,000 kilograms. That's already in kilograms, so we don't have to change it. And just for your sense of scale, that's about the mass of somewhere between a sedan to an SUV. Maybe a light truck. We want to know the net force. And to do this formula successfully, we need to know the acceleration of the car. What is the acceleration of this car?
30 meters per second squared.
It's 0. Because the car is driving at constant velocity. I gave you the velocity and told you the velocity remains at 30 meters per second. By definition of acceleration, A equals delta V over delta T. If the car's velocity is 30 and remains 30, A is 0. So it doesn't matter how fast the car is moving, nor how massive it is. If it's moving at constant velocity, net force is 0. This is what happens anytime you are moving at constant velocity. This is what happens when you turn on cruise control. So this is in reference to law 1 and law 2. If you are not accelerating, Your net force is 0. You can be in motion and have a net force of 0. Now, net force implies that there are individual forces that are adding together. So the next question is, what are some of the forces currently acting on this car? Gravity. Assuming we take, again, if I don't tell you this doesn't take place on Earth, you can assume it takes place on Earth. There's gravity, the car will have some weight. So Fg down is the weight of the car. What else?
Friction.
Friction. I'm going to assume that backwards is, sorry, I'm going to assume this is backwards. So I'm going to label this arrow force of friction. What else? Very good. We're going to talk more about normal force next time, but I'm going to go ahead and write it in. Here, what normal force means is that gravity's trying to pull the car down into the tarmac, and the tarmac is fighting against you. It is pushing up to keep the car from literally falling into the ground. So the earth pushes, the ground's surface pushes up as the earth pushes down. And these two things have to negate each other to prevent you from literally falling through the dirt. If they don't even out, you sink into the ground, which is weird. Maybe quicksand's involved. Now, these are all correct. All these forces are present, and we're going to spend Wednesday and Friday defining them individually, talking about what they mean and how we calculate them. I'm going to add that there is one more, because if net force is 0, all of these need to cancel out. The road up is canceling out gravity down, and that means something has to push forward to cancel out this force of friction backwards. And just to give you the answer, that would be the engine. The engine pushes the wheels and therefore the car forwards to counteract friction slowing you down backwards. That's why if you take your foot off the gas and this goes away, you eventually slow down. I guess we will. All right, we're going to be reviewing this and practicing all week, defining new types of force to add to our list of many forces. Come to lab this week, let me know if you have any questions, and have a great day. All right. So, well, they are related, because Earth's atmosphere only exists because Earth has gravity. If you think about it three-dimensionally, Earth is a ball, and its gravity is pulling air towards it.